Hi, and welcome to the third lecture of the course Machine Learning. Until now, I only mentioned in passing some issues that a data analyst needs to consider when working on a learning problem. For example, feature engineering, overfitting, hyperparameter tuning. In this video, I'm going to go briefly through these and other challenges that have to be addressed before you can initialize your model in Python. Okay. When a product manager tells you, we need to be able to predict whether a particular customer will stay with us or not, and here are the logs of customers' interactions with our product for 5 years, you cannot only just grab the data, load it into a library, and get a prediction. You need to build a proper data set first. Uh, I hope you still remember from the previous lectures that dataset is the collection of labeled examples, xi and yi, for n samples, as you see here, and each element xi in here, for example, x1, is called a feature vector, and a feature vector is a vector in which each dimension, by that I mean this xi1 is one dimension, xi2 is one dimension, and so far and so forth. And each of these dimensions contains a value that describes the example somehow, and the value is called a feature and is denoted with xij, and this example x11, x12, or and up to x1k. The problem of transforming raw data into a data set is called feature engineering. For most practical problems, feature engineering is a labor-intensive process that demands from you a lot of creativity and domain knowledge if possible. For example, to transfer the logs of users that we discussed just earlier about uh, about the user interaction with the computer system, what could create features that contain information about the user and various statistics extracted from the logs. For each user, for example, one feature would contain the price of the subscription. The other one could be the frequency of the connections, or it could also, and that could be per day, per week, per year. You could decide which one you prefer. Another feature would contain the average session duration in seconds or average response time for one request, and many other things. Basically, everything measurable can be used as a feature. And the role of data scientists, data analysts, is to create informative features. And by that, we mean those that would allow the learning algorithm to build a model that predicts well labels of the data used for the training. We call highly informative features are the one that have high predictive powers. For example, the average duration of a user session has high predictive power for the problem of predicting whether the user will keep using the application in future or not. And we say the model has a low bias when it predicts the training data well. That is, the model makes few mistakes when we use it to predict the labels of the examples used to build the model. Uh, some learning algorithms only work with numerical feature vectors. By that I mean that you should and could only input the numerical values. But there are occasions when some feature in the datasets are categorical, like colors, days of the week, and etc. And we still want to use them as our input features. In those cases, in such scenarios, we could transform the categorical feature into several binary ones. And here is a simple example. For example, if you have a categorical feature for colors and this feature has three possible values, red, yellow, green, you can transform this feature into a vector of three numerical values. As you see in this table, red could be 1, 0, 0, yellow could be 0, 1, 0, and green could be 0, 0, 1. And by doing so, of course, you increase the dimensionality of your feature vector. That is why you should not transfer red into 1, yellow into 2, and green into 3, so that we could avoid increasing the dimensionality, because that would imply that there is an order among these values in this category, and this specific order is important for decision making. If the order of a feature value is not important, using ordered number as values is likely to confuse the learning algorithm, uh, because the algorithm will try to find a regularity when there is none, and that may potentially lead to overfitting. What I did here is called one-hot coding, basically transforming the categorical data to the numerical one. And the thing that I said about order is pretty important, so keep in mind, if there is no order important in your data, then don't make your transformation to numerical data project that, because that is going to confuse your model. So that was the situation when we wanted to transform a categorical data to the numerical data. There is an opposite situation occurring less frequently in practice, and that is when we have numerical feature, but we want to convert it to the categorical one. And that we call binning. Also bucketing is another name for that. And that is the process of converting a continuous feature into multiple binary feature called bins or bucket. And this is typically used on value range. Let me give you an example. For example, instead of representing age as a single real valued feature, the analyst could chop ranges of age into discrete bins. For example, all ages between 0 and 5 years old could be put in one bin, 6 to 10 years old could be in the second bin, 11 to 15 to the third one, and so on. So if in our feature vector, you remember the structure of the feature vector, right? We had for our x1, x11, x12, and to x1 cut. So imagine the forced feature where j is equal 4 represent the age. And by applying binning, we replace this feature with the corresponding bins. For example, if we have three new bins, age bin 1, age bin 2, and age bin 3, then we have the added indexes J123, 124, and 125 respectively. And by default, the value of these three new features are 0 at the beginning. Now, if x4, if x I4 is 7, for some example xi, then the new set feature that we have is going to be x1 to 4 equal to 1. And if the age for xi is 13, then x1 to 5 is going to be 1, and so on. In some cases, a carefully designed binning can help the learning algorithm to learn using fewer examples. It happens because we give a hint to the learning algorithm that if the value of the feature falls within this specific range, the exact value of that feature doesn't matter anymore. The next thing that we're going to discuss is normalization, and you probably have heard about normalization in your other courses or during your study when you were building models or even algorithms for the other courses, not necessarily machine learning. So this is a standard practice being done in several different fields. And what is it exactly? For example, suppose the natural range of a particular feature is 350 to 1450. And by subtracting 350 from every value of the feature and dividing the result by 1100, we could normalize the value into the range 0 to 1. if I want to say more generally, this is the formula that we have. Basically, the value you're normalizing, you subtract the minimum number in that range from it, and then divide it over the max minus mean. To put it simply, normalization is the process of converting an actual range of values into a standard range. So this is how normalization done and what is normalization. But there's another question that we want to answer and we're curious about potentially, and that is, why do we normalize? Um, you know, Normalizing as data is not a strict requirement. However, in practice, it can lead to an increased speed of learning. Uh, I hope you still remember the gradient descent example from the previous videos. And now imagine you have a two-dimensional feature vector. When you update the weight parameters, you use partial derivative of the mean squared error with respect to these two weight parameters. And if x1 is in the range that, for example, 0 to 1000, and x2 in the range of 0 between 0.001, then the derivative with respect to the larger feature will dominate the update. So probably the technical things that I explain is not important that much to you. What you need to keep in mind is that we could potentially deal with dramatically different in size ranges, and then the one with the larger range could dominate the whole study that we're working on. Additionally, it is useful to ensure that our inputs are roughly in the same relatively small range to avoid problems with computers that computers have when working with very small or very big numbers, and that is what we call numerical overflow. Okay, this is one of the practices that I'm sure you have heard of. I don't know how much you have applied it in practice, but this is something which is quite important. Uh, the data sets, as I already mentioned at the beginning of this video, do not necessarily come in the shape and form that we require them to come. So they are not as well behaved as we want them to be. And one of the mischiefs that our data sets could have is basically having some missing values. Uh, Let me dig a bit deeper into that. In some cases, the data comes to us as scientists in the form of a data set with features already defined. And in some examples, values of some features could be missing. And this happens often when the data set was handcrafted and the person working on it forgot to fill some values and didn't get them measured at all. So this is something that could happen very possibly, and if you're long enough in this field, you definitely is going to experience datasets with some missing features. So there are some typical approaches when dealing with missing values, and that could be, for example, removing the examples with missing features from the dataset. That can be done if your dataset is big enough, so you can sacrifice some training examples. You could also use a learning algorithm that can deal with missing feature values, and that depends on the library and the specific implementation on the algorithm. You could also use a data imputation technique. And what is a data imputation technique? I'm going to give you some examples here. One data imputation technique consists of replacing the missing value of a feature by an average value of this feature in the dataset. Another technique is to replace the missing value with a value outside the normal range of a value. And this may sound odd to you, but the idea here is basically that learning algorithm will learn what is best to do when the feature has a value significantly different from regular values. Alternatively, you can also replace the missing value by a value in the middle of the range, and here is the idea is that the value in the middle will not significantly affect the prediction, so it is just there. And a more advanced technique is to use missing value as a target variable for a regression problem. Basically, here is to guess what the value is, and then we insert it in our data set in the missing space. Of course, to build a training example, you only use those examples from the original data set in which the value of the feature j is present. And finally, if you have a significantly large data set and just a few features with missing values, you can increase the dimensionality of your feature vector by adding a binary indicator feature. For each feature with missing values, feature value then can be replaced by 0 or any number of choice. At prediction time, if your example is not complete, you should use the same data imputation technique to fill the missing features as you used on the training dataset. And before you start working on the learning problem, you cannot say actually which data imputation technique works the best. What you need to do is to try several different techniques, build several different models, and select the one that works best for you. So it has to do a lot with the practice and what have you seen before in similar cases, and a lot of trial and error until you get to the best data imputation technique useful for your specific problem in hand. So far we talked about the data set. What about the learning algorithm? We discussed about several different techniques that we could get to the most possible ideal data set. How do we choose a machine learning algorithm that we want to use? And I need to be honest with you, this is a difficult task. If you have much time in your hand, you can try all of them. However, this is not normally the case. Normally, you have to solve the problem in a limited time span. You can ask yourself several different questions before starting to work on the problem, and depending on your answer, you can shortlist some algorithms and try them on your data. The first question that you can ask yourself is that, does your model have to be explainable to a non-technical audience? Most very accurate learning algorithms are so-called black boxes. They learn models that make very few errors, like deep learning, but why a model made a specific prediction could be very hard to understand and even harder to explain. Examples of such models are neural networks or ensemble models. On the other hand, k-nearest neighbor, linear regression, decision tree learning algorithms produce models that are not always the most accurate. However, the way they make the prediction is very straightforward. So explainability is one of the first things that you need to keep in mind. Do you need to explain the model or not? The other question is again about the dataset. Can your dataset be fully loaded in the memory of your server or personal computer? If yes, then you can choose from a wide variety of algorithms. Otherwise, you would prefer incremental learning algorithms that can improve the model by adding more data gradually. And we talked already about that in the previous lectures. Again, another question about the dataset is that how many training examples do you have in your dataset? How many features does each example have? Some algorithms, including neural networks and gradient boosting, we are going to talk about them later, can handle a huge number of examples and millions of features. Others, like support vector machine, can be very modest, to put it mild, in their capacity. And again, is your data composed of categorical only or numerical only features? Or it's a mix of both? Depending on your answer, some algorithms cannot handle your dataset directly, and you would need to convert your categorical features into numerical one, as I already explained a bit earlier in this video. And another thing to consider is that, is your data linearly separable or can it be modeled using a linear model? If yes, Support vector machine with a linear kernel, logistic, linear regression could be good choices. Otherwise, deep neural network or ensemble algorithms might work better, and we are going to discuss all these algorithms later. Another important thing is that how much time is a learning algorithm allowed to use to build a model? Neural networks are known to be slow to train, and simple algorithms like logistic and linear regression or decision trees are much faster. Uh, Specialized libraries contain very efficient implementation of some algorithms. You may prefer to do research online to find such libraries when you're doing your modeling. Some algorithms, such as random forest, benefit from the availability of multiple CPU cores, so their model building time can be significantly reduced on a machine with dozens of cores. So this is something that you need to keep in mind, and of course, you could also always think about how you can speed up the process. And again, about the speed, how fast does the model have to be when generating predictions? Will your model be used in prediction where very high throughput is required? Algorithms like support vector machine, linear and logistic regression, and some types of neural networks are extremely fast at the prediction time. Others, like k-nearest neighbor, ensemble algorithms, and very deep recurrent neural networks are slower. If you don't want to guess the best algorithms for your data, a popular way to choose one is by testing it on the validation set. And that is what we're going to talk about later. Okay. Uh, until now, I used the explanation. I use using the expressions dataset, training set interchangeably. However, in practice, data analysts work with three distinct sets of labeled examples. And they are training set, validation set, and test set. Once you have got your annotated data set, the first thing you do is to shuffle the examples and split the data set into three subsets: training, validation, test. And we have already used these terms very frequently during this course, but let me refresh your memory. The training set is usually the biggest one. You use it to build the model. The validation and test set are roughly the same size, much smaller than the size of the training set, and the learning algorithm cannot use the examples from two subsets to build the model. So basically, when you're building your models, you're not touching the validation dataset and the test dataset. And that is why they are often called holdout sets. Uh, I can't say there is an optimal proportion to split the dataset into these three subsets. In the past, the rule of thumb was to use 70% of the dataset for training, 15 validation, 15 testing. However, in the age of big data, datasets could have millions of examples, and in such cases, it could be reasonable actually to keep 95% for training and 20.5 for testing and 25 for validation. And you see that it is already different from the practice we had in past. You may also wonder what is the reason to have three sets and not one or two. And the answer is simple. When we build a model, what we do not want is for the model to only do well at predicting labels of the examples the learning algorithm has already seen. A trivial algorithm that simply memorizes all training examples and then use the memory to predict their labels will make no mistake when asked to predict the labels of training examples. But, and this is a big but, such an algorithm would be useless in practice. What we really want is a model that is good at predicting examples that the learning algorithm didn't see. We want good performance on holdout sets. Basically, we want to be able to use the model for something. The model that is not able to predict unseen examples is worthless. And again, Okay, training is clear. We need more than one set because we want to test our model on. But then why do we need to have two holdout sets and not? We use the validation set to choose the learning algorithm and find the best values for hyperparameters. We use a test set to assess the model before delivering it to the client or putting it in production. And probably I need to make a bit of clarification here. Training data set was clear, and we get good accuracy at some point on during data and training data set. Then we get to our validation data set, and it potentially could not perform as well. We need to start choosing the algorithm differently, tuning the hyperparameters, and this is a back and forth interplay between validation set and training set. And in a sense, we get the validation contaminated. It is in one sense or the other part of our training data set if we have used it for hyperparameter tuning or choosing the algorithm. So we want to have something that the model hasn't seen after we are certain that the model that we built is good and have proper parameters, and that is when we are going to use the test data set. Okay, uh, if you remember, I have already used the notion of bias here and there quite casually, and I said that a model has a low bias if it predicts well the labels of the training data. But if the model does not behave that well, or on the contrary behaves too well, we are going to have two important issues. We could either have underfitting or overfitting. And what do we mean by underfitting, for example? If the model makes many mistakes on the training data, we say that the model has a high bias or the model underfits. So underfitting is the inability of the model to predict well the labels of the data it was trained on. And this could be due to several different reasons. Probably the most important ones are the model is too simple for the data. For example, a linear model can often underfit, or the feature you engineered are not informative enough. And the first reason is quite easy to illustrate in the case of one-dimensional regression. The data set can resemble a curved line, but our model is a straight line. And the second reason can also be illustrated like this. Let's say you want to predict whether a patient has cancer, and the features you have are height, blood pressure, and height rate. These three features are clearly not good predictors for cancer, so our model will not be able to learn a meaningful relationship between these features and the label. The solution to the problem of underfitting is to try a more complex model or to engineer features with higher predictive power. So this was about underfitting, and we say the model underfits and it has a high bias. Another important problem is the overfitting. This is when we say the model has high variance. Uh, the model that overfits predicts very well on the training data, but poorly on the data from at least one of the two holdout sets. Several reasons can lead to overfitting. The most important ones are your model is too complex for the data. For example, a very tall decision tree or a very deep or wide neural network often overfit. Another reason could be that you have too many features but a small number of training examples. In the literature, you can find another name for the problem of overfitting, the problem of high variance. And this term comes from statistics. The variance is an error of model due to its sensitivity to small fluctuations in the training dataset. It means that if your training data was sampled differently, the learning would result in a significantly different model, which is why the model that overfits performs poorly on the test dataset. Testing and training data are sampled from the dataset independently from one another. Even the simplest models, such as linear, can overfit the data. And that usually happens when the data is high dimensional, but the number of training examples is relatively low. In fact, when feature vectors are very high dimensional, the linear learning algorithm can build a model that assigns non-zero values to most parameters for the weight and trying to find very complex relationship between all variable available features to predict labels of the training example perfectly. Such a complex model will most likely predict poorly the labels of the holdout example. And this is because by training to perfectly predict labels of all training examples, the model will also learn to uh, learn all the noises as well. And the noise is the value of the feature. In the value of the feature of the training examples could really hinder the whole thing. Uh, the model you see here, the thing that you see here, basically the graph represents what does underfitting and overfitting mean, and the middle one is the good fit. So what could be done to overcome the overfitting problem? One approach is to try a simpler model, linear instead of polynomial regression, or support vector machine with a linear kernel, or a neural network with fewer layers input units. Another way is to reduce the dimensionality of the example, for example, by using some dimensionality reduction techniques. We could also add more training data if possible. And finally, we could do regularization or regularize the model. And that brings us to the topic of regularization. And what is regularization? It's another tongue twister. Is an umbrella term that encompasses methods that force learning algorithm to build a less complex model. And we are going to see a bit of regularization in our hands-on practice today. In practice, it often leads to a slightly higher bias but significantly reduce the variance. The problem is known in literature as the bias variance trade-off. And the two most widely used type of regularizations are L1 and L2. And the idea here is quite simple. I try to put it in words. Hopefully you can catch it. To create a regularized model, the model that has less chance of being complex, we modify the objective function by adding a penalizing term whose value is higher when the model is more complex. So basically, by adding this penalizing value, this penalty, we force the model to favor the less complex ones. And it could be applied to a variety of model. Let's see the example of linear regression. Probably that is the easiest one. If you remember, this was the linear regression objective function. Basically, we wanted to minimize this error value. And an L1 regularized objective function looks something like this, where you see I added a CW value in the function, where W is defined as you see here, and C is the hyperparameter that controls the importance of the regularization. If we set C to 0, the model becomes a standard non-regularized linear regression model. On the other hand, if we set C to high value, the learning algorithm will try to set most WJs to a very small value or 0 to minimize the objective. And the model will become very simple, which potentially could lead to underfitting. And the role of you as data analyst is to find such a value of the hyperparameter C that doesn't increase the bias too much, but reduces the variance to a level reasonable for the problem at that hand. Okay, this was L1 regularization. What about L2 regularization? It is very similar. to the previous one. In practice, L1 regularization produces a sparse model, a model that has most of its parameter equal to 0, provided that hyperparameter C is large enough. So L1 makes feature selection by deciding which features are essential for predicting and which are not. And this can be useful in case you want to increase the model explainability. However, if your only goal is to maximize the performance of the model on the holdout data, then L2 usually gives better results. L2 has also an advantage of being differentiable, so the gradient descent can be used for optimizing the objective function. And of course, you need to have the general idea about these two different things, and then you're going to libraries to perform that. So it's probably the underlying formula is not that much important for you, but it gives you an understanding why things are working the way they are working. L1 and L2 regularization methods were also combined in what is called elastic net regularization, with L1 and L2 being special cases. And you can find other names in the literature for them as well. For example, you can see that L2 is called rich regularization and L1 is called loss. In addition to being widely used with linear models, L1 and L2 regularization are also frequently used with neural networks and many other types of model which directly minimize an objective function. There are also two other ways to regularize neural networks, and they are dropout and Bayes normalizations. There are also non-mathematical methods that have a regularization effect, data augmentation and earlier stopping, and we are going to see many of these methods in the future videos, but for now just know that these things also exist. Okay, once you have a model which our learning algorithm has built using the training data set, how can we say that the model is actually good? And then here is when we need to use the test set to assess the model. The test set contains the examples that the learning algorithm has never seen before. So if our model performs well on predicting the labels of the example from the test set, we can say that our model generalizes well, or simply it is good. To be more rigorous, machine learning specialists use various formal metrics and tools to assess the model performance. For example, for regression, the assessment of the model is quite simple. Well-fitting regression model results in predicted value very close to the observed data. The mean model, which always predicts the average of the labels in the training model, generally would be used if there were no informative feature. The fit of a regression model being assessed should be better than the fit of the mean model. If this is the case, then the next step is to compare the performance of the model on the training and test dataset. And you have seen these things in the previous lecture. To do that, we compute the mean squared error for training and separately on the test dataset. And if the MSE on the test dataset is substantially higher than MSE on the training dataset, then you're overfitting. Regularization, or better hyperparameter tuning, could solve the problem. And when I say substantially higher, I mean basically it depends on the problem at the hand, and it depends really on you to decide which one is the best one. So this is for regression. And how about the classification? For classification, we are going to use several different things. It's a bit more complicated than regression. I'm going to list them here, and then I'm going to go through them one by one. We could use confusion matrix, accuracy, precision recall, area under curve, and to simplify, I probably will use some binary classification that is extendable to other multi-class classifications as well. So let's see what is the confusion matrix. The confusion matrix is a table that summarizes how successful the classification model is at predicting examples belonging to various classes. One axis of the confusion matrix, as you see here, is the label that the model predicted, while the other axis is the actual label. In a binary classification problems, like what you see here, we have two classes, and let's say the model predicts orange and not orange. And the confusion matrix that you see in this example will say that 105 examples that actually were orange uh, also predicted correctly, and the model also correctly classified here 15 not orange as not orange. So the other two blocks that are left are the wrong predictions. The confusion matrix for multi-class classification has as many rows and columns as there are different classes. It can help you to determine mistake patterns. For example, a confusion matrix could reveal that a model trained to recognize different species of animals tend to mistakenly predict cat instead of panther or mouse instead of rat. And in this case, you can decide to add more labeled examples of these species to help the learning algorithm to see the difference between them. Alternatively, you might add additional features to the learning algorithm that can use to build a model that would better distinguish between these species. So this was confusion matrix. What about precision and recall? Precision is the ratio of the correct positive prediction to overall number of positive predictions, as you see in this formula. And recall is the ratio of correct positive predictions to the overall number of positive examples in the data set. To understand the meaning and importance of precision and recall for the model assessment, it is often useful to think about the prediction problem as a problem of, for example, research of documents in the database using a query. The precision is the proportion of relevant documents in the list of all returned documents. The recall is the ratio of the relevant documents returned by search engine to the total number of relevant documents that could have been returned. In the case of a spam detection problem, for example, we want to have high precision. We want to avoid making mistakes by detecting a legitimate message as a spam. And we are ready to tolerate lower recall. We tolerate some spam messages in our box. Almost always in practice, we have to choose between a high precision or a high recall. It's usually impossible to have both at the same time. We can achieve either of the two by various means. For example, by assigning a higher weighting to the examples of a specific class. For example, the support vector machine algorithms accepts weighting of classes as input, so it depends on the algorithm as well. Or by tuning hyperparameters to maximize precision and recall on the validation set. We could also use varying the decision threshold for algorithms that return probabilities of classes. For instance, if we use logistic regression or decision trees to increase precision, and that is at the cost of lower recall, we can decide that predictions will be positive only if the probability returned by the model is higher than 0.9. Uh, Even if precision and recalls are defined for the binary classification case, you can always use it to assess a multi-class classification model. And to do that, first select a class which you want to assess with these metrics, then consider all examples of the selected class as positive and all other ones at negative. So it's basically one against everything else. So this was two metrics, precision and recall. There's another one that I'm sure you have heard a lot about it, and that's accuracy. Accuracy is given by the number of correctly classified examples divided by total number of classified examples. Accuracy is a very useful metric when errors in predicting all classes are equally important. In case of spam, non-spam, this might not be the case. For example, you would tolerate, as I said, false positive less than false negative. A false positive is in a spam detection is a situation in which your friend sent you an email, but the model labels it as a spam, doesn't show you. This is not what we want. On the other hand, the false negative is less of a problem. It's basically detect a small percentage uh, of spam emails or messages as the healthy one, and it's not a big deal. We could then get rid of them ourselves. Okay. So now we get to another performance matrix, and that is the area under the ROC curve. The ROC curve stands for Receiver Operating Characteristic, and the term comes from radar engineering, probably that's not important. And this is a commonly used method to assess the performance of classification models. ROC curves use a combination of true positive rate, defined exactly as recall, and false positive rate, and that is the proportion of negative examples predicted incorrectly, to build up a summary picture of the classification performance. ROC curves can only be used to assess classifiers that return some confidence error or probability of prediction. For example, logistic regression, neural network, decision trees, and ensemble models that are based on decision trees can be assessed using ROC curves. The higher the area under the ROC curve, and that is what we call AUC, the better the classifier. A classifier with an AUC higher than zero point 0.5 is better than a random classifier. If AUC is lower than zero point 0.5, then something is wrong with your model. A perfect classifier would have an IUC of a 1, and ROC curves are popular because they are relatively simple to understand. They capture more than one aspect of the classification by taking into consideration both false positive and negative, and allow visually with low effort comparing the performance of different models. When I presented learning algorithms, I mentioned that you, as a data analyst, have to select good values for the algorithm's hyperparameters for gradient descent. But what does that exactly mean? Which values is the best, and how we could find it? And I try to answer these questions here. As you already know, hyperparameters aren't optimized by learning algorithm itself, and this is up to you to tune the hyperparameters by experimentally finding the best combination of values, one for each hyperparameter. One typical way to do that when you have enough data to have a decent validation set in which each class is presented by at least a couple of dozen examples, and the number of hyperparameters and their range is not too large, is to use grid search. And grid search is most simple hyperparameter tuning technique. You use a training set and train a few models, let's say 14, one for each combination of hyperparameters. Then you assess the performance of each model on the validation dataset using one of the metrics we discussed before. And finally, you keep the model that performs best. So the idea is simple. Train several models, test them on validation dataset, keep the best one. And that is what we call grid search. Once the best pair of hyperparameters is found, then you can try to explore the values close to the best one in some regions around them. So after you chose the model based on the previous steps, then you can play with the values very close to the ones that you have. Just a bit higher, a bit lower, probably you can find something best. And sometimes this can result in even a better model. And finally, you assess the selected model using the test dataset. As you could notice, trying all combinations of hyperparameters, especially if there are more than a couple of them, could be time consuming, especially for large datasets. So these are not necessarily very efficient. So grid search is the simplest one, but not necessarily the most efficient one. There are other ways. For example, we could do random search or Bayesian hyperparameter optimization. And random search differs from grid search in the sense that you no longer provide a discrete set of values to explore for each parameter. Instead, you provide a statistical distribution for each hyperparameter, from which values are then randomly sampled and set the total of number of combinations that you want to try. Bayesian techniques yet again differ from random and grid search in the way that they use past evaluation results to choose the next value to evaluate. And the idea is to limit the number of expensive optimizations of the objective function by choosing the next hyperparameter values based on those that have done well in the past. Okay, we talked a lot about validation set, test data set, training data set, and we in most of the cases we assume that we have enough data to play with. But what if we don't have a decent validation set to tune the hyperparameters on? In this case, the common technique that can help is the cross-validation. When you have few training examples, it could be prohibitive to have both validation and test dataset. You would prefer to use more data to train the model, and in such cases, you only split the data into training and test dataset. And this is when you could use cross-validation on the training set to simulate a validation set. Cross-validation works like this. First, you fix the value of the hyperparameters you want to evaluate. Then you split your training data set into several subsets of the same size, and each subset is called a fold. Typically, five-fold cross-validation is used in practice. With five-fold cross-validation, you randomly split your data into five folds, F1, F2 to F5. And each FK, for K between 1 and 5, contains like 20% of your training dataset. Then you train 5 models as follows. To train the first model, F1, you use all examples from folds F2, F3, F4, and F5 as a training set, and the examples from F1 as a validation set. To train the second model, F2, you use F1, F3, F4, and F5 to train. And F2 as a validation set, and they continue building iteratively like this and compute the values of the metric of interest for each validation set from F1 to F5. Then you average the 5 values of metrics to get a final value, and you can use grid search with cross validation to find the best values of hyperparameters for your model. And once you have found these values, you use the entire training set to build a model with the best values of hyperparameters you have found via cross-validation. Finally, you assess the model using the test dataset. By this, I wrap up the part for the best practices, and in the next video, I'm going to talk a bit about neural networks. See you in next.